take this form, okay? There is one Krauss operator that we clump together that's close to the identity, and it has some corrections of order dt, and the leftover stuff we call proportional to the effective Hamiltonian. So it's basically looks like time propagation that we're familiar with for unitary evolution, but with an effective Hamiltonian that has a imaginary part, okay, or an anti-Hermitian part. And then the remaining Krauss operators would have to be proportional to the square root of dt. And that's kind of beautiful, I think, because that just, from those basic principles, tells us that the time evolution, if it's going to be Markovian, then it must have the form of the Lindblad master equation. And the Lindblad master equation is this, and it can be written as a differential equation, and it's written in many different ways. They're all equivalent, but it's important to kind of go back and forth in your head between them. There's this form, which has something that looks like the Schrodinger evolution, but with a non-Hermitian Hamiltonian, and then this other term here. And this term includes Hamiltonian and decay, or dissipation, and this term is what we call refeeding. That refeeds population coherences sometimes in a way that's trace preserving. The separation, one of these terms came from this Krauss operator, and these refeeding terms come from these other Krauss operators. That's going to have some important conceptual meaning and also calculational meaning in thinking about its relationship to the measurement model, right? Because we said every Krauss operator is related to having done some measurement on the environment and then using the quantum Bayes rule, how we update the state conditions on that measurement. Keep all those thoughts in your head, we'll come back to that. So if we unpack this a little bit more, we can separate out the Hamiltonian, the unitary part, which is here, and everything that I might call dissipative. And that's the Lindblad superoperator, which has this form. So these are all just different ways of saying the same thing. We write this in different ways in different applications. And the other thing that we showed at the end of last lecture is that we can think about what these Lindblad operators are by looking at rate equations for populations in the absence of any coherent driving. And so the matrix element, the square of the matrix element of this Lindblad operator tells me the rate at which quantum jumps happen between those states, those basis states. They might be energy levels of the Hamiltonian, for example. And if I look at the total rate at which I leave state J, that's the matrix element of L dagger L. That's for a given decay channel that's labeled by this index mu. We can have multiple ways that jumps can happen, for example, labeled by the polarization of a spontaneous photon, for example. And then the total rate would be the sum of all possible partial decay channels. Okay? So these L operators are sometimes called the Lindblad jump operators for that reason, because they have some interpretation in terms of quantum jumps. And we'll come back to that. The quantum trajectory method that I've alluded to goes by many names because it was developed sort of simultaneously by a number of different schools of thought, and sometimes it's called the quantum jump method for this very reason. Okay, we'll come to that a little bit later. Okay, so this equation was just written down as, and if we're going to have such a map that does this, this is the form it has to take, but we didn't derive it from first principles. We just wrote it down, said let's pretend there's a Krauss map that does this, what would its form have to be? And then we found this is what its form was. The damn spam keeps calling me, stop that. All right, so, so we want to think about the derivation. Now, as we have discussed, we're never going to be able to get, this is never an exact description. It's an approximate description, because this, the equation of motion for the state is not time reversal invariant, whereas we know the complete description is, that has to be time reversal invariant. So this derivation has some important approximations, and it's always going through this, can always be a little bit, feels like the wind is blowing you over with all the hand waving that's happening, but we'll try, okay?
Fast and infinitely slow.
Right. So let's maybe just first motivate this by thinking about, so, you know, the derivation of the master equation is really is it follows from coarse graining. The time evolution. That means we have some coarse grain of time, delta t. That's not a differential, it's something finite. That, you know, kind of looks like delta t, but that's not exactly true. There's some finite grain of time. It's coarse, it ain't fine. And all of the irreversibility is buried in losing track of information that happens in this coarse grain. The information is kind of removed in these coarse grains. Okay? Otherwise, we couldn't have something that was irreversible. Now, in order to do coarse graining, what's required for coarse graining is a separation of time scales. Well, that's really the key story in this derivation, is that there are two very, very different time scales that are important in the problem. And one is so separate from the other that one can be considered infinity and the other can be considered zero. Okay, so let's motivate that. So the scenario is that we have the environment and we have the system. Okay, and we can motivate this and think about the quantum derivation, just thinking about standard kind of Boltzmannian thermodynamics, where sometimes the environment is also called the bath or the reservoir. Because the scenario that we're thinking about is we have some system and we bring it in contact with a reservoir, which typically we would think about as being in a thermal state at some temperature T. And then we want to bring the system in contact with the bath, it was literally a bath. You put the thing in it and it would equilibrate in some way. These guys would come into equilibrium with the environment. Now, of course, if T goes to 0, that's the vacuum. And we'll come back to that. So even at 0 temperature, we can have an equilibration of sorts. Of course, in that case, the system would go to its absolute ground state if it was at 0 temperature. So, the picture is, okay, here's my, the reservoir. It's a big reservoir of water. Here I am, my excellent artistic skills. And I got a hot penny. Ow! Which I'm going to throw into the reservoir, which is at some temperature T, and I drop it in. It's at a different temperature. It's going to re-equilibrate, right? I mean, and the penny is so tiny compared to this reservoir that the penny barely changes the temperature of the reservoir. We can neglect that. The reservoir can be considered effectively infinite in its number of degrees of freedom, which are the water molecules, compared to the penny, that I don't have to worry about the fact that this thing is going to heat it up. And the penny's going to come. How does the penny come into equilibrium with the reservoir? What happens, of course, is that there are water molecules that bounce off this penny, and they will carry away some of the kinetic energy of the penny, and the water molecule momentum will be correlated in some way to the vibrational state of the penny, but very soon this guy is going to collide with other molecules in here, and in some sense the correlation between the momentum state of the water molecule and the vibrational state of the penny is quickly scrambled or completely lost in all the multiple collisions that it has with the Avogadro's number of water molecules, sitting in this thing. So there is an important time, which I'll call TC, which is the correlation time of the system and the reservoir, or environment, or bath. Okay? That time is going to be incredibly short if this is a macroscopic system compared to another time scale, which I'll call T relax, or dissipation, which is the time scale over which the system comes into equilibrium with the reservoir.
So the penny is your system.
That's right. My penny is my system, not me. I put some glasses on there so you know it's me. Sort of, anyway. This is the environment. Okay. And the idea is that these two scales are very, very different. This time is incredibly short compared to this time. It'll take many, many, many collisions of an individual water molecule with the penny before it comes into equilibrium with the reservoir. And so the fact that this guy is huge compared to this means we can look at the time dynamics of the equilibration of this penny in a time scale that I'll call a coarse grain of time delta t, which is effectively infinity compared to this, but 0 compared to that. That's the whole story. That if the system possesses this very big separation of timescales, then I can coarse grain and treat delta t as a differential with respect to how the system is evolving, because it's so small of a grain compared to the timescale over which the system is changing. But it's effectively infinite time. The system has lost its memory. So that is the timescale over which the water molecules recollided and lost any correlation with the system. Okay?
So I have a question. When you, for tau c correlation time.
Yep.
Correlation of what?
So it's a good question. It's the correlation of the system and the reservoir.
In temperature.
Well, it's the correlation of their state. So as to say, is there any information, how much information about the vibrational state of the penny remains in the motional state of the molecule? It's there in principle, but it's gotten so mixed up because it collided so much, it's basically, they're uncorrelated. So if I were to look at the motional state of the molecule, it would look like it was completely uncorrelated. If I look at some momentum correlation function, it would decay over time, and the time scale over which that correlation would decay would be set by tau c. And it would be incredibly short compared to the time scale over which the penny changes its state, which is its vibrational motion state. Because it requires many collisions before it comes to equilibrium. In this particular example. This is just one example, but it's illustrative of the whole story. Okay? So with that beautiful cartoon in mind, we can then try to now formalize this mathematically. So the idea, we have the system in the environment. That's everything in the world. And so there is a Hamiltonian of the system in the environment, which is some Hamiltonian for the system, some Hamiltonian for the environment, and some interaction between them. Okay? So this Hamiltonian only acts on the system degrees of freedom, this Hamiltonian only acts on the environmental degrees of freedom, and that's the Hamiltonian describes the coupling between the system and the environment. And we want to look at the evolution of the joint state of the system, and then the state of the system is what we get when we trace out the environment. So we need to look at the dynamics of how the system and environment are coupled together, and then trace out the environment, and then get an equation of motion for the system evolution. Okay? Now it's convenient to do this in what's called the interaction picture, where when you're looking at this kind of interacting system, it's good to go to the interaction picture, in which we take the free evolution, uncoupled evolution of the system and environment, and take that out of the dynamics of the state and put it into the operator. Okay? So in the interaction picture, the interaction Hamiltonian is time dependent, evolving evolving according to the free evolution. It's not really so important, these details. And, you know, we will think about this as being of the form of there's some operators A for the system and some operators B for the environment. They might have a bunch of different ones. Okay, so I'm going to assume my interaction Hamiltonian couples system degrees of freedom and environmental degrees of freedom. There's some product of operators that couple those together. Okay?
So that middle agent is at time 0?
Yeah, and it's in the Schrodinger picture, which is it's time independent, which is the same thing as at time t equals 0. So in the interaction picture, the joint state of the system evolves according to the Schrodinger equation only due to the interaction Hamiltonian, because the free evolution is put into the operators and the time dependence of the state is due to the interaction Hamiltonian, okay? So that's the interaction picture. And then the formally speaking, we would have this. We trace out the environment and we get the time evolution of the state of system. Now this isn't really of the Markovian form yet. We have to get there. To solve this problem, we have to have some initial conditions. So we assume at time t equals 0, the joint state is whatever the system is uncoupled from whatever the environment state. So time equals 0 would take the system and the environment to be uncoupled from one another, okay? Like before I threw the penny in. They were uncoupled and then I throw the penny in, all right? Typically we might call this a thermal state. A state of thermal equilibrium, for example. Now, what happens at a later time? Well, at a later time, these things will become correlated. And that's kind of part of the problem. However, in a coarse grain of time, which is big compared to the correlation time, those correlations should be lost for the reasons that I discussed a little bit earlier. So that's going to be the way we'll get at this problem. So let's look at this solution. Let me write down. Right. So let's look at this. We have that the system environment, this is just a formal integration over some finite time delta t. If I integrate this, what I get is this is equal to what it was at time t, and then an integral from t to t plus delta t. Oops. So I just took this equation and I integrated it from time t to t plus delta t, okay? And that's just a formal solution to this thing. Right. So now what we can do is iterate this and get what's known as the Born-Dyson series, for reasons I'll explain in a moment. So let me just plug in for rho t prime, given this expression, and I get that the joint state of the system and the environment at a later time, t plus delta t, is what it is at the initial time. And then I have the first order term, but now at time t. But I'm going to get a correction to second order. So I go from t to t plus dt, t prime, but then t double prime goes from t to t prime, h in t, oh, this should be int, yeah, the interaction Hamiltonian, at time t double prime, h int at time t prime, and then rho system environment t double prime. Okay. So right now I haven't, this is what's known as the Dyson series. I have to re-plug in for t double prime, and then I get a third order term. The first order correction to this is just replace this with rho t, and this is what's called, you know, there will be a third order term, a fourth order term, etc. This is what's known as the Dyson series. The Dyson series tells me a perturbative expansion of the evolution in when I'm looking at small values delta t for a weak interaction, okay? And so if I just truncate this at this level, this is the Born-Dyson series to second order. It's called the Born part of this is from the Born rule that people thought about in scattering, where I have a weak interaction. So this is really potentially familiar to you from the theory of time-dependent perturbation theory, where I think about weak interaction of the system with some external forces, and I look at a perturbative expansion. It's going to be perturbative because I'm looking at short times, and over these short times, I assume the interaction is sufficiently weak. Okay?
So real dumb question, your brackets are the commutator?
They're commutators,
Yeah, okay.
indeed. So commutators that came from the time evolution,
Okay.
and then I just iterated this equation.
Yeah.
Yes, sir.
What if the interaction's strong? Does it have?
Then this doesn't work. Okay, so the derivation of this kind of master equation will only follow if the interactions with the environment are weak compared to the interactions that define the system itself. So for example, if I think about an atom, interacting with black body radiation or the vacuum. What I want is that the binding of the electrons to the nucleus is a strong force compared to the dipole forces that are the electric field that are driving the atom. So there's an assumption here that the interaction is perturbative, is weak compared to the forces that define the system itself. That's the typical kind of perturbation theory we think about in time-dependent perturbation theory. Right, okay, so, all right, so now what? Well, there's two important, there's a number of approximations that we're doing. As I say, at the initial time, the system and the environment are uncorrelated, but at a later time, what I can say is that let's say at time delta t. One coarse grain later, I can always break up the actual state as a part that is, the marginal of the joint system and tracing out the system. So these are the marginal states, or the reduced density matrices of that, plus whatever's left over. Okay, this is not actually a state necessarily, but it's whatever's left over. We call it delta. So the first approximation is that when delta t is much, much bigger than the correlation time, we neglect this. After each delta t, the system and the environment, which are grain that's sufficiently coarse compared to delta t, it's basically infinity compared to delta t, we've lost the correlation, just like the penny and the water molecule's momentum correlation function has become factorized, okay? So that's the first thing that we do. The other thing is that the environment basically is unaffected by the system. And it's basically equivalent to, if we come back to this cartoon, the water, there's some water waves, they're flowing in here. There's a kind of fresh copy of the water coming in at every time. The fact that the penny caused a few of the water molecules to collide with it doesn't really affect the macroscopic state, and a fresh copy of the environment comes in at each time. So it's really the environment, we can break up the environment itself into a bunch of its own subsystems. And I can think about, there's different copies of the environment coming in. Here's my system, and at each delta t, a fresh copy of the environment is interacting with it and passing through and becoming uncorrelated. Is the wind getting you yet?
That's kind of hand, that's pretty hand wavy.
Yeah, and treat this as, after each time scale, the environment basically has been affected. I'll give you another example when we're going to see. Let's say we have the atom interacting with the vacuum, the quantum electromagnetic vacuum. What's going on? Well, there's I can think about a temporal mode, a little wave packet. Here's my atom. My Bohr atom, right? And then what happens, and this atom has, you know, an angstrom Bohr radius or something like that, right? A Bohr radius. And so what's the time scale over which the quantum vacuum fluctuations are correlated with the atom? What would you say?
Over C.
Yeah, it's the time it takes light to propagate across the atom, right? That's, you know, an attosecond or less, right? At that point, that vacuum fluctuation has passed through and the next one comes in. And it looks just like the previous one. And it's gone at that point. And so I can think about it as just, at each time scale, it's the same old vacuum. The fact that I might have emitted, there's some probability amplitude of emitting a photon, but it's going to be a tiny chance in that attosecond that I emitted a photon into that first wave packet, because we know it probably takes a nanosecond or 15 nanoseconds, you know, for the thing. So every one of those things, it almost barely changes. The atom was in the excited state. After that first wave packet passed through it, basically nothing happened to the atom. The time scale over which the atom decays is the one over it's the decay rate, right? It's the lifetime. And that time scale is huge compared to the time scale over which that one little degree of freedom was correlated to it. Okay? So it's not really hand waving, it's what actually happens in the physics. It's harder to describe mathematically.
How fast is vacuum flowing?
At the speed of light.
Oh, it is.
Yeah. Why wouldn't it? Everything. I mean, it's still going at the speed of light. That's what, as Alex said, the time scale. If I think tau c is this divided by the speed of light, that's an attosecond. All right. So I have a bridge to sell you if you want. No. Right. Not the one in Baltimore. I don't want to see that. Okay. So with that, we can say, okay, let's substitute in this, saying that at any time t in our coarse graining, the system and the environment of any time scale I'm going to look at that's going to be coarse compared to the correlation time is this. It's a very good approximation. In any one of these coarse timescales. All right? And now I look at this system by tracing out the environment. Okay, I'm going to take the trace of the environment on both sides of the equation. And then I'll get what the system is. The first term, when I get then, is that the system at time t plus delta t is, well, the lowest order, it's what it was at the time t. Then I'm going to get, I substitute in, I'll just write that in over here. Right? This is system at time t, tensor environment at time 0. When I take the trace over the environment of this term, so then maybe I'll just write it out. So that's sums of h bar t to t plus delta t dt prime trace over the environment of H system and the interaction Hamiltonian system environment minus the trace over the environment system environment interaction. Plus second order. Maybe I don't need the second order, maybe first order is enough. What about this term? Well, the interaction Hamiltonian I said was of the form of, you know, a sum over some possible terms, some system operators coupled to some environment operators. Right? That's my interaction Hamiltonian. And when I take the trace of this, what I'm going to get for this term over here is something that looks like the sum over all these operators, the expected value of the system times the expected value of that, where that's the trace of this with this, and that's the trace of that with that. Do you see that? The other thing that we typically assume, although it's not at all necessary for the derivation, is that whatever the system operators are, I'm sorry, this should say environment. Whatever the environmental operators are that couple to the system, so this is the mean value of that operator for the thermal state, or whatever the state of the environment is, that typically this is 0. We'll come to look at that example. Let's say the mean field of the environmental operators that couple to the system will typically be 0 for the states of interest. We'll look at an example of that in a moment. But for the moment, we'll just consider those cases where whatever those things that couple for the thermal state of the environment, their mean is 0. They have fluctuations. Their fluctuations will be critical. The fluctuations of the environment are critical. I mean, the example, a simple example is vacuum, where the operator might be the annihilation operator that takes that, or creation operator that creates and annihilates a photon. The mean of A or A dagger is 0. There's no mean field. However, the fluctuations in the field are what's causing the decay. So that's the typical example we consider, and in that case, which is why we need to go to second order. That's why we keep the second order, because the first order term typically vanishes. If it didn't vanish, it would just give you some mean first order evolution due to the mean driving, but typically that wouldn't be like a reservoir. A reservoir typically would have 0 mean field. It's the fluctuations that matter. Yeah?
Can we also say something like, so it's, that first order term is a commutator.
Yep.
If you took the full trace of that commutator, it would be 0. We're not taking the full trace, so we're only taking the environment.
That's right.
Trace.
It would,
The
well,
result
if
of
the-
it will be, the result of it, you know, even before we're saying it's zero, is still going to be something with trace zero. Is there something mathematically we can say like, okay, because this is a trace zero, and because of something else we can ignore it?
well, the trace of this would equal the trace of this. These terms, I mean, if I took the full trace, all these terms vanish because it's a trace preserving map.
Okay.
The partial trace of that term was not necessarily zero. It wouldn't be zero if this had a mean field. It would look more like a Rabi driving of the system due to the mean field of the environment, okay? But if there is no mean field, this term vanishes. And that's if it didn't, we would just subtract it out and put it into the Hamiltonian in the first place. So we got to deal with this term. And I screwed up my board, so say loud.
Before you cover that board, I have a question. So that the low order terms are a good approximation when delta t is small compared to the timescale defined by the eigenvalues of those Hamiltonians. So should we think of those as like a relaxation time, like h bar over the eigenvalue or the max eigenvalues of those commutators?
It's a little bit more complicated because, you know, the time dependence here is very important. So it's not just the eigenvalues of the interact Hamiltonian itself, but something about the way in which they're evolving with the free field evolution. There's some, I mean, we'll see what that time scale is in a moment, but I don't think it's fair to say that they're just due to the eigenvalues of the interaction Hamiltonian.
Well, it would be the eigenvalues of the commutators, but I see what you're saying. It's more subtle than that.
It's a little bit more subtle than that, yeah. All right, let's write down then our expression for here. Right. So what I have is that the system at some coarse grain time delta t later, which I obtained from tracing out the environment of the joint state, is approximately equal to what it was at time t. And then the first correction is second order in the interaction Hamiltonian. So I get minus I squared is minus 1 over h bar squared, integral t to t plus delta t, dt prime, integral from t to t prime, t double prime, trace over the environment of the double commutator. That's what, so what approximations did we make so far? A, we made the perturbative expansion. We only kept this up to second order. That's the second order is the first non-vanishing correction. That was one approximation made. And then the other approximation we made was the fact that the system and the environment decouple at a coarse grain time that's big compared to the correlation time, and that the environment is unaffected because it's effectively a very big system. So if we subtract this from the other side and divide by delta t, I get delta rho over delta t is approximately equal to minus 1 over h bar squared, the integral from t to t plus delta t, dt prime, the integral from t to t prime, d double prime, and then I'm going to expand out this double commutator, and when I do that, I can group terms in the following way. There's going to be terms that look like this: h int at t prime, h int at t double prime, rho system at time t. Oops, sorry. And then I'm going to get a term that looks like this. And then I'm going to get a term that looks like this, and a term that looks like this. So let me write it all down, and then let me explain what we're looking at and what these different symbols mean. Okay, so what is this expression? What I did in this expression is that I expanded out the double commutator, and then I took the trace over the environment. This expectation value sub E means the trace of this operator with the state of the environment. Okay? So that's what this means. This guy over here is the trace of that operator with the state of the environment. Yes?
So I think I must have missed, why did the first order, because like in the rho SE term, we originally had like just a single commutator.
Exactly. Yeah, the point was that went away. So here's that term. I wrote it out. This is the first order commutator. And then I just plugged in the form of the interaction Hamiltonian. And I said, let's consider the case where the mean field is 0. Then the first order term is 0. And that's what I was trying to argue, that's typically the case, that when we're talking about something that is like the environment or the reservoir, it's really doesn't have a mean field, but it has fluctuations. In the same, and an example of that is black body radiation. If I look at the mean electric field, there's no mean electric field, but there are fluctuations in the electric field. So the first order correction is second order. The first order correction just goes to 0.
Also, just to check, why is it h int t double prime first and h int t?
Well,
prime
why did
second
this
in
come
the
like
first
this?
term? Yeah, and then it switches on the next one.
Well, I was looking at the commutator. So that's h times rho minus rho times h. That's the first order commutator. That's just the commutator, h times rho, and then rho times h.
But on the next word, the second order commutator term has ht prime, ht double prime, right?
Oh, why did I do that? Maybe I made a mistake. Thank you. Yeah, that's wrong. Hold on a second. yeah, this is wrong. Yeah, because when you iterate the Dyson series, it goes like that. Okay, but I want you to take a peek at this equation. Is it reminiscent of something? We got row sandwiched between things, and then we got two things multiplying row on one side and the other added together. So we kind of sort of begin to see the structure of the Lindblad equation beginning to emerge a little bit, right? This is somehow going to be related to the jump operator pieces and the L dagger L pieces sort of sitting there, okay? This is, at this point, you know, a fairly generic form that one could start with, that for an arbitrary system, I could say, to the degree to which I made these approximations, the Born approximation, lowest order perturbation theory, the decorrelation time, I haven't said anything about the nature of the interaction other than the mean field was 0, okay? So now, to make any progress, it's better to look at some specific examples. So let's do our example that we've alluded to, which is a two-level atom in a black body radiation, okay? So let's look at the problem of the system being a two-level atom. And the environment being black body radiation. Okay. So we have our system. We're only looking at two energy levels. We'll call one the excited state, the other ground state. There are system operators that we can think about as Pauli operators associated with that two-level system. We have sigma plus, we got sigma minus, we got sigma z as system operators. And the environment is defined by the modes, which have creation and annihilation operators associated with a particular plane wave mode, for example, the sort that we studied last semester, right? And we'll take the state of the environment to be a thermal state. So, firstly, what is the mean of this operator in the thermal state? It's 0. There's no mean field, right? What is that? That's the number of operators, so that's the mean number of photons in that mode, which depends on that frequency, and this is the Planck, right? So this is the mean number of photons at that frequency given the certain temperature, right? What is that. AA dagger. Do the commutator dance according to Coles?
1 plus n, right?
1 plus n, right, or n plus 1. As the temperature goes to 0, what's the mean number of photons? 0, right? At 0 temperature, this thing goes to the vacuum at t equals 0. That's the case when the temperature is 0. That's the case of the two-level atom interacting with the vacuum. And at that case, this would be 0, but this would still be non-zero due to the quantum fluctuations, which is the commutator. Okay. All right. So what's our interaction Hamiltonian? So, we have h of the atom, which depends on, say, whatever the excited state. The h of the field, which is the environment, which is the sum over all modes, h bar omega, a dagger a. We don't care about the half because that plays no role. And the interaction Hamiltonian, well, we make the dipole approximation is minus d dot e, right? And we did that last semester, and you plug in the expansion of the electric field operator in terms of the plane wave modes, and you make the rotating wave approximation, which is a good approximation, and you get a sum over coupling constants I'll call G, a dagger, a sigma plus H. So this is the quantum optical expression for the interaction of the atom and the field. And we recognize it as the terms that we think about it as resonant or energy conserving, where I absorb a photon and therefore annihilate it. And in the process, I go from the ground state to the excited state. Or I emit a photon, which is creating one in the field, and I lower the atom from the excited state to the ground state, okay? And this coupling constant is what we call the vacuum Rabi frequency, which is the coupling of the electric field, which has a strength that is the square root of h bar omega divided by the quantization volume, with the units of Gaussian units, because you're stuck with me. And then the dipole dotted into the polarization of the field e to the I k dot, the position of the atom. Now this comes to your question, Brandon, about under what circumstances is this a weak coupling? The coupling of the field to the atom, when can I consider that to be weak? And so weak I can ignore it. Firstly, this should be, this energy scale, which is the energy associated with the electric dipole coupled to the electric field, should be small compared to this energy scale, which is related to the binding energy of the electron. But the other thing has to do with how big this dipole matrix element is. Maybe it's even 0. For example, suppose I have you know, an atom that's an S state, and my excited state is a D state. This has L equals 0, this has L equals 2. That's, you know, spectroscopic notation, SPD, right? There is no dipole matrix element here because these two states have the same parity, and there's no, if I looked at the dipole associated with the distribution of the electron around the nucleus, it would be 0. There'd be no electric dipole.
But that just means your exchange was improper.
That's right. So that means really I should think about the quadrupole interaction of the field. The first non-vanishing multipole moment is not dipole, in that case it's quadrupole, which would mean this would have a very long lifetime, right? It's a metastable state. It would take a much longer time for this thing to decay. Or maybe it's a magnetic dipole. And there's also something about the frequency that will play a role. Let's say the wavelength of this transition that will play a role, that has something to say, because we remember our classical electrodynamics, and the rate at which we get Lomer radiation depends on how fast the thing is accelerating. There's still physics. I don't care about jumps, there's still physics. And the charges have to accelerate to radiate. If their frequency is low, that means they're accelerating not very fast, which means the rate of radiation is very, very slow. So if I have, for example, a hyperfine transition, which is at a microwave or between two Rydberg states that are separated by a microwave rather than an optical frequency, that's a very long-lived, there's going to be almost no spontaneous emission between those. Or maybe it's a magnetic dipole. So there's lots of things that come into that determine how important. This comes to your question, Victor, about when I create a closed system. If I think about an atomic clock and I have the two clock states of cesium, there is no spontaneous emission that I care about because the time for that to happen is so long. It's millennia. The coupling strength is a magnetic dipole. It's at a gigahertz scale and it barely radiates. So yes, it's an open quantum system, but for all intents and purposes, it's closed, which is why we use it as an atomic clock in the first place, because it's got an infinite lifetime for all intents and purposes.
Without the quantization volume, you know, if you have some very small little.
Yeah, I can also try to modify with cavity QED, and the Purcell effect can affect those things as well. Absolutely. As studied in homework. All right, so let's continue. Oh God, time flies, I'm having too much fun, this is not good. And we're supposed to finish this today. Christ. All right, well, we're not gonna. Right, okay, so with that said, let's look at the interaction Hamiltonian in the interaction picture. So I have to look at the free evolution of this and the free evolution of that. This thing in free evolution goes like e to the minus I omega t, and this thing goes like e to the plus I omega atom t. So what I end up with, I can write this in the following way. F sigma plus F dagger sigma minus, where F of t is equal to the sum over all the modes, G, the coupling constant, e to the minus I omega k minus omega of the atom Right. This operator is sometimes known as the reservoir noise operator. I can think about the fluctuating field as kind of a noise source, a noisy field, a non-coherent field that is interacting with my system, and that fluctuating field, that noisy field, is what's causing dissipation and irreversible evolution. What's important in this, in thinking about it, if we write down, I'm just going to write down a couple of more equations, and then when I plug this into this expression at the top, I get the following. In this case, the atom system, its coarse-grained time evolution, plugging in let's look at this equation. And all I did to get to this equation is I plugged in to the top equation this form of the interaction Hamiltonian in the interaction picture. What I see already Lindbladian form kind of beginning to emerge here. But importantly, what I have over here are what are called the reservoir noise correlation functions. They tell me something about how the fluctuating noise correlates with itself at different times. The whole story will be to try to show, well, it's not the whole story, but it's the end of the story, is how this thing in the Markov approximation is delta correlated. So that I can think about it as there's basically no time, after almost no time, this thing is correlated with itself. So if this becomes a delta function in time, then I get the Markov approximation. And that's basically saying that this is white noise. To the degree to which I can treat the reservoir as white noise, I get the Markov approximation. If it's color, if it has a finite spectrum, we call it colored noise, and that would give me something that would have a memory kernel in it. It would say that what happens at one time doesn't just depend on what the atom state is at that time, but over some time interval. I'd have to take into account a non-Markovian bath has memory, but like my increasingly aging brain, you lose memory, and eventually it becomes zero, and that's
There's
sort of
there's
it.
somewhere
What's that?
It's not still out there.
It's
somewhere.
out there. In principle, there's a course variant. So anyway, we'll finish the story next time and show how, how we can see under this important picture, which was really the key to the whole story, this coarse graining of delta t being very big compared to a correlation time, but a short time. All right? All right, very good. We'll continue it next week.